Hello, dear students. Welcome to the channel and very welcome to this playlist in which we are discussing 8085 microcontroller in detail. Up until now, we have seen architecture, we have seen pin diagram, we have seen arrangement of different buses in 8085. We have also discussed the memory organization in 8085. And today, we are going to discuss about the typical configuration of 8085 microcontroller, and then we will move further with programming. So about this configuration, before we move directly to the configuration, let's see the preliminary interfacing devices. And most probably we will only be discussing these devices today, and we will be discussing the configuration in upcoming classes. So first device is the tri-state logic, and tri-state logic are often called tri-state devices as well. And as per its name suggests, it's not very difficult to guess that it contains total three logics: high, low, and high Z, which implies for high impedance condition. So when the device is in the tri-state, or whenever device is in the tri-state condition, which means high impedance condition, the connection before that device and after that device is electrically disconnected, right? So see, this is the tri-state switch. It includes input, output, and an enable signal. And the truth table indicates that it have three states. When D in is X and when enable is 1, the output will be high Z, which means high impedance condition. And when D in is 1 and enable is 0, the output will be 1. When everything is 0, then output will be 0 as well. Isn't it obvious? Now let's see the second one. It's called buffer, and many of you might be familiar with buffer. It's a logic circuit used to increase the strength of the driving capability of my line. So buffer increases the power, right? Which means buffer increases the current of the line. So when we select the buffer, it gives respective output. But when we do not select buffer, it makes the line it makes lines in high impedance state. And every single buffer line is capable of sourcing 15 milliampere current and sinking 14 milliampere current as well. But there are these two buffer ICs which are very popular uh, among the users of microprocessor. First one is the internal 74LS244, and another one is 74LS245, right? These two ICs are very popular. So uh, in short, I'm going to call them S244 and S245. So S244 is a unidirectional buffer. It has two groups of four buffers. As you can see, we have uh, 1, 2, 3, and 4 buffers, and they are divided in two groups, C 1 and 2, right? Each group is controlled by enable line 1G and 2G. As you can see here, we have two enable lines. This is 1G, and second one here we have 2G. And the internal structure is shown in this image here on the left hand side. Then we have this S245, which is actually a bidirectional buffer, and it is used to increase the driving capability of my data bus. And because of that, they are often also called octal bus transceivers. You can see the internal structure of S245 in on the right hand side of this slide. So it consists of 16 non-inverting buffers, and you can count all of them here. Actually, pins we are giving here. not exactly buffers, but you can count them. So starting from 2 to 9, and then it goes from 11 to 18, right? So 16 non-inverting buffers, 8 for each direction with tri-state outputs. And the direction of the data flow is controlled by the dir pin. When dir is high, the data flows from A bus to B bus, and when dir is low, data flows B to A, right? So this dir pin controls everything. Then active low enable signal and the dir signal are ended to activate the bus lines. As you can see, the end operation is taking place between both of them. and each buffer can sink 24 milliampere and stores 15 milliampere of current, right? Just like tri-state devices. Now here you can see the truth table for that. We have 1G, 1A, 1Y, 2G, 2A, 2Y, and different inputs are giving us different outputs. The the values of um, Z is the same as tri-state device, and 1 and 0 are doing obvious jobs of there. 1 indicating high and 0 indicating low. See, when G is 0 and dir is also 0, the data is flowing from bus B to bus A. When G is 0, dir is 1, the data is flowing from A to B. And when G is 1 but dir is X, then it is an isolation condition. So what are the features of this bidirectional switch or bidirectional buffer? So bidirectional bus transceivers is holding high density 20 pin package. So tri-state output drives the bus lines directly, and hysteresis at bus input improves the noise margins. Except that the PNP input reduces the DC loading on the bus line, and typical propagation delay time, typical propagation delay times port to port is around 8 nanoseconds, so it is drastically reduced. Typical enable disable time is also again 17 nanosecond, again very less. And sync current and source current that I have already discussed with you. Now let's discuss the next one, the latch. So latch is also often called the D type flip flop. It is actually a D type flip flop, and it is also called D-Latch. And uh, it is indicated by IC 74373, right, or IC 74LS373 often called. It is an 8-bit latch. It has the D-type flip-flop and provides the buffer controller input, right? So it is providing the controller input to the buffer. Except that it provides choice of 8 latches or 8 D-type flip-flops in a single package. As you can see here, we have 1 2 3 4 5 6 7 8 D-type flip-flops in one package. And it has tri-state bus driving output. It has full parallel access for loading. It has a buffered control input, and it has PNP input that reduces DC loading on the data lines. So here in the image you can see the chip that 8-bit register features to totem pole tri-state output that are designed for capacitive or low maintenance loads. The 8 latches are D-type latches that indicates that when enable is high, enable is basically this G switch. G switch is my enable, and when Q output, the Q outputs will follow the D input, and when enable is low, the output will be latched at the level of the data that was set up. Okay, so it's a bit confusing, so I'm repeating it one more time. So when the enable is high, when G signal is high, the q is my output, so q will follow the d input. D is my input. Q will follow the D input when enable is high, and whenever enable is low, the output will be latched at the level of the data that was set up. Okay, so it will be latched at the level of data that was set up, and it will be much clear when we go through this truth table. So see, when G is 1 and D is also 1, the output is 1. Output control is 0. When G is 1 and D is 0, that means what is happening, it will follow whatever D has, so 0 again. When there is no input from D and there is when Z is 0, then it will hold the previous output Q0, the level of the output before the steady state input condition was established, right? So basically the previous output, or the level of the previous output where before the steady state input condition was established, it will hold it. And when there is no input uh, and no enable, the output control will hold 1, which means it will go into the high impedance state. And this high impedance state Z and increased high logic level drive provides these registers with ability of being directly connected and drive the bus lines in the bus organized system without pull up of any registers. So the output control pin of this 34373 can be used to place 8 outputs in normal logic state or high impedance state. You can put total 8 outputs in either of the state, either normal logic state or high impedance state. But what happens in the high impedance state, the output neither load nor drive the bus lines very significantly. So it does not affect the internal separation of latches or internal separation of flip-flops, and because of that the old data can be retained or new data can be entered whenever the outputs are off in these conditions, right? Now let's move forward and let's see the decoder. So here we have the decoder as well. You can see decoder in the image. Basically decoder is the digital logic circuit that converts n-bit binary input code into m number of output lines. As you can see here, these are my n binary inputs, and this is my m output lines. Each output line will be activated for only one of the possible combination of inputs, and it will not be operated otherwise. And you can see this one is the generalized block diagram of decoder. Whenever you go and whenever you search for decoder, you will find this diagram. So the number of input lines are n, output lines are m. As you can see, n is the input, m is the output. And decoder, n can be any integer and m is the integer that is less than or equal to 2 raised to n, right? Because you have to set up the combinations, so the number of m should be an integer that is less than or equal to 2 raised to n. So m less or equal to 2 raised to n because possible codes are there, and one of the m lines will be activated depending upon the combination of codes, and then other lines will be deactivated. And active logic can be low or high, depends upon the chip. Let's see one of those chips here. There's a chip called 74138, which is a 3 by 8 line decoder. Again, see, 3 by 8, which means in order to identify the value of m, what do I have to do? 2 raised to n. What is n? N is 3. 2 raised to 3 equal to 8. So my output is 8. So that is why we are having 3 by 8 line decoder. So this decoder, 3 by 8 line decoder, or which is also called IC 74138, is widely used in microprocessor or microcontroller based systems, and you will find them very frequently whenever you work on microcontrollers, even on microprocessors as well. So it's a high speed 1 of 8 decoder or demultiplexer. And let's see different pins and let's see the pin diagram of it. We are having 3 inputs which are address inputs or select lines. The name of the pins are ABC. Then we have 3 enables. You can see here 4 5 6. We have E1 minus E2, G2A, G2B, which are the enable inputs which stay actively low. Then there is G1, this enable line 5, enable line 6, not 5. That is the enable input that remains actively high. And then we have the active low outputs starting from O0 to O7 in the output line. Then we have the VCC for the supply voltage, and there is a ground which we find generally in most of the chips. So this chip is a 16 pin chip with ABC select lines to select required output line to be active, and two inputs two inputs are active low enable inputs is in, and there is an active high enable input as well, and then finally 8 active low inputs. And to understand that, we can also see the truth table. So here is a truth table, and here you can see the 3 inputs A, B and C. There is 3 enables G1, G2B and G2A, and based on the different conditions and different inputs of ABC and G2A, G2B and G1, we will be obtaining different outputs, right? Where H indicates the high voltage level, A indicates LSB, C indicates MSB, least significant bit and most significant bit. L indicates low voltage level. Here you can see low voltage level making a trace, and X stands for immaterial, right? So initially we are having ABC as XXX and GA is X. Only G2A is high voltage, and as an output we will be getting everything high voltage. Same thing will happen when G2B will become high voltage. Everything will be high voltage. Now here's the interesting thing. Still A, B, C are immaterial. G2A and G2B will be immaterial, and when G1 will be low voltage level, the still O0 to O7 will remain in high voltage, and when everything is low but G2B is high, still everything remains high voltage. See, which means in order to keep maintained every high voltage everywhere, you have to keep either of this enables either immaterial or high voltage. Now see, here from here on we are getting all low voltage. We are keeping only G1 high voltage, A high voltage, and B and C low voltage. So O1 will be low voltage, OO will be high voltage, and others will be high voltage. And after that, significantly, we will be getting trace here, and based on the change in the condition of A, B, and C, the enable is not changing here at all, right? So you can follow the table, you can understand it. We will be moving forward with the next topic. So next one is the demultiplexer. Here we are demultiplexing address and the data bus. So the address will appear 80 to 87 on the lines, and ALE or address latch enable will go high, forcing the enable become 1, and it will make 74LS373 latch transparent, Hence, whatever will be the input, that will be output. So if presently input is address A7 to A0, so output will be A7 to A0. And before address disappears, the ALE will become 0. And due to this contents in FF, it will get latched. And even though input toggles, the output will not change. Thus, till the next cycle, unless next ALE appears, the status will be latched and will not change at all. So now AD0 to AD7 will be continued as a data bus and will be labeled as D0 to D7 only. Now from A15 to A8, we have pure or high order address bus, and thus the output of the latch A7 to A0 upon the upper apologies on the upper order address in total will provide us 16-bit address A15 to A0. Thus this stage we are at this stage we will be ready with A15 to A0 address bus and D7 to D0 data bus. Now how do we generate the control signal? So control signals are not directly available for reading and writing the data from memory or input output devices, but it contains the input output memory to differentiate between memory and input output devices in order to read data and write data. And by using these lines, we can generate four-step signals that read or write for memory and read or write for input output devices. So the control signal required are the active low, and we call them MEMR, memory read, and MEMW for memory write. And then we have IOR, input output read, and IOW, input output write. So the truth table for that you will be able to see, you have seen already in previous classes, in previous class only, so you can check it out in previous class. And then there is another truth table based on the active output line. So when the condition on input output memory equal to 0 and read is also equals to 0, see here, and write is equals to 1, it represents the memory read. Sorry, it represents the memory read control signal. Now for these combinations, the output line is active, so first output line of 3 by 8 decoder can be used as a MEMR signal or memory read signal. And similarly we can go for this combination, input output memory equals to 0, read is also equals to 0, and write is equals to 1. So second output line will be activated and MEMR signal will get MEMW signal. Then we have IO memory equals to 1, read equals to 0, and write equals to 1, right? So the read equals to 0, write so the fifth active output line will be activated and input output read will be activated. So the 3 by 8 decoder and its connections are visible here. So, and it will operate in the similar fashion that we have discussed. So we will keep today's class till here. If you have any doubts or queries, feel free to discuss them in the comment section below. Any kind of feedbacks are always welcome. You can submit your feedbacks in the comment section below as well. So I will be seeing you next time. Thank you very much for listening. Goodbye for now.